Alright, so true story.
I was gonna flip it off, but then I realized wait, that was probably not the
Yeah, that's not cool. Then I have to like stop the recording and like delete it and restart it. Alright, so we do have a lesson to cover today, and you're gonna need the worksheet from yesterday that has the back of it with the like speakers on it. But first, I wanted to throw a real problem at you guys because it will end up on Desmos with this. And this is a true situation. So my brother-in-law is probably... Huh? I don't know.
Your brother-in-law is starting up a startup?
Well, he's about to become
He's an
part of a startup.
accountant and doesn't know his answers right. He's not a mathematician.
So my brother-in-law is an accountant.
No,
He's a very smart accountant. But there are some differences between accountants and mathematicians and like what we learn. So he'll talk about things and I'm like, I have no idea what you're saying, bro. And I'll talk about things and he's like, yeah, I'm not sure if we ever use that sort of stuff in accounting. So there's some differences, right? So he called me up yesterday and threw this problem at me. None of this is made up. It's all real. I actually solved this like last night with him to double check work.
Was he right?
It doesn't matter. Like, he had solved it multiple different ways. He was trying to figure out which one was correct. So yes, one of the ways he had solved it was correct. But the problem is cleaning it up is the hard part. So what we're dealing with here is they want to be able to pitch to their, like, investors or whoever, like the board, right, what a client will end up being valued at. So this is... simplest way to say it is like a software company that your business, your big old business, like bigger than a couple people, mom and pop shop, would be paying on average $9,022 for an annual usage of this software and all their tools and everything else. Now that, because of cost of living increase and improvements to the software, is going to inflate by 7% each year. What does it mean to inflate something? To grow, right? Increase it. So we're going to...
How much is annual? Is that yearly?
Yearly. Yep. So they'll be charged like once a year, like January 1 or whatever you want to say. Like once a year they'll be charged. The second year they'll get charged more because the software will be better. But anyone who just purchases their software on year 2 will be paying that new price, right? So $9,022 is like the price for right now. We'll say January 1st, 2022, right? If somebody buys the software. But the company's not up and running quite yet. So all of this is slightly hypothetical. So by the end, we should be able to change this number if we get a clean formula. We should also be able to change this number. And we should also be able to change how long they're with us, because this is really what is going to make this complicated. Is they're going to stick with us for multiple years. Because when people adopt a software, guys, think about MAP, right? Our grading software. Are we going to stop using this version of MAP next year? No, that would be silly. We're going to use it for a while, but until it comes outdated. So they're saying, let's assume that somebody will stick with us for 7 years, but it could be shorter. They could bail after 5 years. They could stick with us for 10 years. So here's your question. What will be the lifetime value of the client at the end of their total time with us? And more so, question in bold, can you create a clean equation to model this, like in Desmos or in your TI? And the real reason that I'm having you guys do this is to figure out if you've learned about this special mathematical shortcut or not. Okay.
3 variables.
Okay.
I can do it. Well, 4. I can do 2 variable equation. You can do it 2 variables. With all of it being able to change?
Right now, you can use these numbers, but by the end, when we type it into something, we should then be able to modify the numbers, right? So we don't need to necessarily write an equation that involves a variable for like the initial cost and the percent value, but we should be able to, in our equation, change those numbers, right? Like physically, just like go in and change those numbers. So what we're looking for, what my goal last night seriously was to be able to create a graph that shows if somebody sticks with us for 5 years, here's what they will have been worth after the entire 5 years. If they stick with us for 7 years, what will the entire 7 years of value from them have brought in? If they stick with us for 10 years, right? So we should be able to follow the graph in Desmos and see what their value, the total value was.
Yeah, I don't think they could.
So one of you said something, right?
I said it was an exponential function.
So it's not an exponential function, but it's not just.
It's like those continuous, cause it's like the PR and then I don't know what it's called.
That sounds really complicated.
E and then to the power of RT, something like that formula.
It is not compound interest, where we have to use E. So E is like Euler's number, right? It's actually a value. E is a constant. So we just use E when we need that number. There's a specific purpose for E. This is not going to use E.
What about the A times 1 minus R over N to the power of N times T? Well, I don't really know.
Wait, why doesn't Desmos graph that?
You're on the right track.
What did you put down?
But remember, specifically, what I'm asking is when we compute the end value, it should tell us the sum of all of the years they've been with us, right? So year 1, year 2, year 3, all the way to their final year, and then add all those up so we can predict if this person stays with us for 7 years, how much will they be worth? This is like real world. I hate using that phrase because it gets used in the wrong way. This is real world stuff, guys. Like, this is happening right now.
We could use a
Literally.
recursive formula. That'd be really easy.
What do you mean we could use a recursive formula?
Oh, like T of n equals T of n minus 1 times plus equals it's T of n minus 1 and then it's plus 9,000 times 1. Right?
So you're saying if year 1 was 9,022 or whatever it was,
Yeah.
then the second value would be
9,022 plus 9,022 times 1.07.
plus 1 point.
No, it's just it's
What did you put? I feel like,
well, yeah, but that's a recursive equation. Well, not exactly how you wrote, but that's basically a recursive equation. Because you have to x minus 1.
And then what Jake keeps putting in front of me is 9,022 times 1.07 to the x, which
it's
here we're assuming is 7.
But that doesn't take into account. That's like how much you get from the individual year. That's not
Ah.
lifetime stuff.
So wait, we need 1, 2, 3, 4, 5, 6. Man, I should have just made one more blank spot. So that's year 1. Let me just erase these and make another blank spot. Year 1, year 2, year 7.
No, wait, it's actually 1.07.
That is 1.07.
No, it should be year 1 plus year 2. It should be.
Oh, so you're saying we need to do 1 plus 2.
Yeah, and then plus 3 plus 4.
So we're not just writing, so 3, 4, 5, 6.
Is this permutation?
So year 3, year 4, year 5, year 6.
And then each of those is just 1.07 to the number minus 1.
So each of these is 9,022.
Times 0. It's J's equation except for the x minus 1.
Why is it x minus 1?
Because the first time we started with just 9,022.
Oh, so over here, 9,022 times 1.07 to the 0th, because there's no inflation applied to the first year. Jake, does it motivate you if I tell you haven't found the answer yet?
You're way
And I have something to teach you? Okay, you're spacing out, staring at geometry.
I'm thinking.
So wait, if year 1 actually uses the power of 0, I'm just kind of making notes. What power does year 7 use?
Also,
6,
it's
right?
-1. That's what Jake put up.
Okay, so this uses 6. So you said these are all x minus 1s. But I gotta add up 7 things? Do you? Genuine question. This is why I thought about, like, oh, hey, I should do this with these guys.
Is this a logarithm? I don't know.
Do you know what
Come on.
this?
Oh! I know what that is. It's a loggy thing.
That
I've
looks
seen those
like a
before.
fish in a
Yeah,
mouth.
someone told me about what that is.
Oh,
I don't
yeah,
remember
you're
what
right.
it's called.
Epsilon.
Greek letter, but I don't
Is
know
it
what it is.
epsilon?
Which one it is or what it stands for.
So that Greek letter is sigma.
Oh, I was gonna look up a Greek alphabet.
Google sigma notation.
I think there's an Overwatch character named.
I mean, Greek letters get
It's
used for a lot of things.
Okay.
Math is fun.
Math is fun.
It indicates
No, that's the name of the
summation and is used as a shorthand notation of the sum of terms that follow a pattern. For example, the sum of squares. Yeah, that's what it is.
Huh?
That's what it is. I say stuff.
I don't understand.
Okay, then look at this. I don't.
Start at this value, go to this value. Huh?
Oh, that makes sense.
What makes sense?
What they said. Start at this value, go to this value. But I don't
Okay,
know
start at that value, go to that value. Woo!
how you write it.
And
But
then-
what?
I don't know how you write it.
Ooh,
Wait,
I get to teach you something.
the vectors in this? It looks like it.
That doesn't sound
Can
right.
you
Me?
explain it better than this random
I
website?
can. We. Thank you for
That's
asking.
his job.
Makes me feel good. We want to add up a bunch of stuff.
Right.
And actually, there's a famous story about Einstein where he and Einstein didn't have calculators, right? Einstein's teacher was kind of annoyed with him, and who knows if this story is true or not, but you can imagine if Einstein was your student, he'd probably be kind of annoying. So his teacher said, all right, Albie, we assume, it's Albert, Albie. She said, all right, Albie, go ahead and head over in the corner, whatever. Add up all the numbers from 1 to 100, 1,000, a million, whatever you want to put in there, however long you want to think Einstein was busy. And very quickly, Einstein comes back. Says, here you go. And the teacher, perplexed, says, it would take much longer than that to add up all these numbers. He goes, I didn't. Didn't add all these numbers, but he got the right answer.
How though?
Because it's like the 1 and 99 is 100, and then like the 2 and 98 is 100, so you go up to all the way up to like 51 and 49, and then there's a 50, and then, yeah.
So the problem is, what you said, everything you said is true. The problem is, that's a linear relationship, right? So when we're talking a sequence of integers, that's linear, right? We're going to add by the same thing each time. So you're right, that's what Albert did, Albie. That's what Albie did, but what we're dealing with here is exponential, right? So we're effectively saying the final year of investment or final year of like the client being with us would be $9,022 times 1.07, and you guys said to the x minus 1 because the first year doesn't happen, right? The first year doesn't have inflation applied to it. So then, with sigma notation,
Why does it look like that?
with sigma notation, what we do is say, hey, start at 1, or you can start at 0 or wherever you want, and go to, if we want it to be an actual function that relates like
Wait,
X and Y input, and then we would need y equals. Open up Desmos.
I found it.
Open up Desmos. So Jake's gonna need a computer, which I can't believe I'm having to ask Jake to get a computer out.
Yeah, that is weird.
The real reason, well, there's many reasons why I'm doing this. I wanted us to look at how to change the settings on Desmos as you guys are getting deeper and deeper into Desmos, and I know some of us might get bored over winter break.
Why can I not put an x minus 1 up here? Oh, you have to put it in parentheses.
Silly.
Well, wait, how did you get the sigma? Are you in the graphing calculator?
Yes, there's a functions button.
Where's the functions button?
Oh, you click the keyboard.
Okay.
And then there's a functions button. And then you click miss. Well, I just went through all of them. But
Oh, there's a so much easier way.
wait, huh?
Type in sum.
Some?
Literally, if you type in SU, watch. As soon as you hit M for sum. Now, you can use N or I or whatever notation down here you want. It's just telling us where to start. So we're going to start at 1.
Wait, you clicked SU and enter, right?
S-U-M.
Oh.
Sum.
Oh.
And
That looks weird. It's like
we could say we're going to stop at 7. But it's better if we're going to try to change and modify and look at like, well, they might be with us for a different amount of time than 7. Let's make this X. It doesn't really look like anything.
It looks like a right angle.
So,
It's like a line.
9,022
No, it looks like a right angle.
times, I like parentheses,
I just have a line.
Yeah,
See,
same.
I have a right
And
angle.
it like stops right after 0 and just extends infinitely past.
Mine was
to the power.
Yeah, it's a right angle.
Man, I wonder if he's doing this on purpose. I wonder if this is like failing on purpose. Or at least goofing up, not failing. But first things first, I like to always clarify that yes, I'm going to be graphing a y equals, just to make sure that my calculator or whatever's doing the right thing.
That's how mine looks like.
And yeah, so this doesn't look great. It's very confusing.
I'm zooming out.
Well, not very confusing, but... Oh, wait. Zooming out. Here's the problem with Desmos. When I just, like, wheel clicks zoom, what's happening with the X and the Y? The same thing, right? If we simplify what's happening, they're the same thing. Go over to the right. Click on the gear, the wrench.
No y-axis.
Open graph setting.
Wait, what? Oh. Graph 7?
Settings.
Oh.
I'm tired of wearing masks. Our x-axis is modeling our what? What did we set up our x to be?
Years.
Years that they're with us. So do we need negative years? Nah. Set your x to 0 at the minimum.
Whoa.
Maximum years, they might maybe, even if I want my graph to just model like not way further, but further than it might go, I don't know, 15? 10, sure, whatever. Y-axis. We should probably start at 0 because most of the time we like starting at 0. But if I'm thinking realistically for Y is... So pause for a second, and we're not in a Desmos activity where I can pause you. But if they invest $9,000, not invest, but like purchase, like pay, like $9,000 every year for between 1 and 15 years, but yeah, our max is going to be like talking about 10 or 15 or however far, we need a pretty high Y maximum value. Yeah, so set it to be something big.
It's a step function.
But it's a weird one.
It's
Why?
no.
Why is it like that?
Oh, because exponential, don't.
Wait, huh? Is that because of the notations then? Because it only counts the integers, it doesn't count the... Is that it? Huh?
Whoa! That's cool. When you zoom out.
Wait, and the lines get steeper and steeper and steeper.
Yeah, they do. It looks like a
It looks like a plane, like a lane.
Here's our notation issue. Sigma notation wants to use the variable that you've referenced. So n is actually the variable we referenced. We're going to use n in our power, but n will turn into x at the end of whatever x is.
Now it looks flat. Oh, that makes sense. It makes sense when it looks flat.
Why would that make sense?
Because it only goes up like yearly. It doesn't
Ah,
go
what
like
sort of
that.
function is this?
Step function.
What do we actually call it?
I don't know.
Starts with a P.
Permutation.
Now, this might be on your test next week.
Partial.
Piecewise. So this is what we call like piece, like P-I-E-C-E. This is a piecewise function. Now check it. Look up here. No joke. This is what I sent my brother-in-law last night. What if they, instead of inflating by 7%, only inflate by 3%? And let's turn on the 7 years that they said, okay, let's assume 7 years. If you inflate by 3% every year, the total value of that client would be predicted to be $69,000. But if we inflate by the 7%, $78,000 is the total value of the client. If the client's with us for 8 years instead of 7 years, you go from 78,000 to 92,500. So imagine being able to take this sort of visual to your board of investors and say, if we set up a system where we inflate by such and such % each year, start our base value. Now, if we want to change our base value, we can just go into Desmos and change our base value, right? We just change this number. Just change the function.
90,000.
So let's make it 9,500. And then our values will reflect that, right?
That doesn't look right.
What do you mean?
Oh,
What-
never mind.
Like, I would need to change this one, too, if I was going to compare.
Oh, yeah.
Compare and contrast.
So, guys, what I'm really trying to get through to you here, you'll never stop using this stuff. Like, depending on what career you go into will depend on how heavily you use it. But, like, I sent the link to Desmos to my brother-in-law, Chuck. Like, literally, I was like, here, it's a visual, right? It's a sweet visual. Look at if they're with you for 10 years. 124,651. That's not just 9,000 times 10, right? Because of that inflation value. But the step between each of these gets larger and larger, right? Because that 7% of the base value keeps growing as the base value keeps growing. Because the whole point of this was, one, to brag that I got to help my accountant brother, and two, to show you summation notation. So sigma is extremely powerful.
Good afternoon, Phoenix. Before lunchtime, could we please have Lily Hayes stop by the
Nobody
office?
cares.
Lily Hayes, please
Well,
stop
Lily
by the
probably
office
does.
before lunch.
I'm wondering if
Thank
her
you.
lunch just got dropped off at the office, and now that's why Lily needs to go to the
Yeah,
office.
probably.
Alright, so, real life math aside, we'll come back to doing more stuff like this later in the year. Let's do some math. Yeah, good work, guys. So sigma, your TI also does this. Your TI calculator can also do sigma notation. So if you are looking for a shortcut to add up a bunch of stuff, you can use sigma notation.
I'm still not quite sure I understand it.
What is, so we put this wrong here, and this can be n or I or whatever.
Wait,
So-
no, I. The square root of -1.
Not here. Here they're just using any number as a value of what are we going to start at. So yes, sure, we might as well just make this n. We're saying n starts at 1, but if I don't put an n over here, it doesn't make sense, right? So I could call this x starts at 1 and goes to x, but that's kind of like, that doesn't quite model quite right. So it's better to say n is going to start at 1. I'm going to use n right here, say n minus 1. and then we'll go to x so that x can be a variable, right? So it can change for how long are they with us. Does that make a little, like, this doesn't need to make total sense right now. I just really wanted to show you guys sigma notation. Because I realized, like, oh, they might not know sigma notation.
And then, so can you just put, like, 1 plus n in there or something?
Just play with it for a second if you want. How could you add up the numbers from 1 to 100? You already did it? What do we do? Sum. Start at 1, end at 100,
Okay,
and then just make this n.
Desmos looks ugly. I think I have the thing in right.
Guys, depending on what you type into Desmos, there's just one answer.
5,050.
Yeah, because the sum of the first 100 numbers is 5,050. It's not a function unless I make something variable. Like, what if I say instead of 100, if I make this the sum of the first x numbers?
Wait, why is 1 plus n not work?
It does. Wait, what?
Oh, it's because my graph settings are still so... I should open up a new Desmos and go back to default graph settings. Or I should turn this off and just go back to default. Check this out. Sum of the first x numbers.
Step function.
Step function again,
Piece bar.
right? 3, 6, like... Look at this.
Awesome. Yeah. So cool.
Sum of the first 22 numbers, 253.
That's kind of cool.
Some of the, like... Yeah, it is kind of cool, right? Like, it's a mathematical shortcut to do math I don't want to do. I know how to add things. Make the computer do it for you.
Wait. Huh? You have the parentheses.
Now here's the problem. I can't just let you guys play with this. We have to actually do a lesson. Pull out that worksheet from yesterday. Don't worry, this shouldn't take too long.
Learning is for noobs.
So, don't worry. I'm going to segue. It's going to be great.
Segue?
Yeah, I'm going to get on one of those little carts and zoom around. Okay, never mind. So, the point of why Chuck actually called me was not that he couldn't do the math. Obviously, he could write down 7 different values of the client cost and add up 7 years' worth of values. It was cleaning it up to be efficient. Got the worksheet from yesterday. So, mathematics is all about efficiency. And as you become, a member of the quote-unquote real world that teachers like to talk about,
No, that's what
money becomes very important, and stuff is mildly important, depending on how much you care about stuff. So we have Laura asking us to help her with her sound system. Now, I've got some personal opinions about Laura mounting her speakers at different heights, but Laura and I already had it out, and she said, I am putting my speakers where I want them.
aesthetically not pleasing.
You are correct. It is aesthetically very bothersome to me.
And also I feel like it's bad for your ears. Unless, like...
So we'll assume there has to be a reason, like a window or something like that, obviously the picture doesn't show that to be true, but then it tells us speaker A is located 6 feet above, speaker B is located 4 feet above. We're just working with that no matter what. Let's say maybe she already put holes in her wall. She's stuck mounting the speakers there. She doesn't want to spackle, doesn't want to paint. You got to put the speakers there. So if you've ever looked up speaker wire, which you probably haven't because we're living in 2021 and you guys have Bluetooth. If you've ever looked up speaker wire, it's expensive. It's just metal wire, but because it's carrying sound, high quality speaker wire is very expensive. If you want some evidence, go look up Monster wire or whatever, not right now. It's hundreds of dollars for a coil,
How long's the coil?
I don't know what to call the thing, but the thing it comes on is 50 feet, 100 feet, whatever. Yes, thank you. It's hundreds of dollars, for real. And this is what they use, in schools and everywhere else. All of our PAs are hooked up with wire. All of our, most things aren't Bluetooth because it can get interference. That's where building cost comes in. So what Laura needs us to do is minimize her costs. And minimization, yeah, I think that's a word, is often a task put to mathematicians. So your job is to figure out where to put the head unit, which is what you call like the actual receiver, or receiver you can also call it. The thing that controls the music, right? The receiver, the head unit, whatever you want to call it. Where should we put that and run those wires diagonally to be the shortest amount of wire that we
Do
actually
we have to put it on the ground?
Let's assume that she can run the wire behind like a piece of art or something where running the wires diagonally doesn't matter. Who cares about aesthetics? If we're saying this wire costs like $20 a foot, which that's not outlandish, she doesn't care about what it looks like. She wants to buy the least amount of wire she can.
Well, then we can make triangles.
That's what he just said.
You are right. That is what I just said.
I'm sorry.
You're fine. So we can make triangles, maybe something like this.
That's something triangle.
All right, so Desmos helped us out here, right? Hey, look, it all ties
It
together.
told us the answer even.
They did, like, this is just here. It's not, that's not the answer.
What we know, what we want is we want the speaker A distance and the speaker B distance.
It's like, is here, well, what, like this. If we just say, well, forget it, put your head unit on the left side, this would be 6 feet. Right? How would we find out?
Pythagoras' theorem.
Ooh, the cult. We gotta use the math cult. So we got 4, 8. Oh, that's not. Yeah, because 64 plus 16, square root of 80, add those up if somebody would. What is square root of 80 plus 6? Let's do decimal approximations. Even though we don't love decimals, let's use decimal approximations because we're going to order this.
After this, are we going to go to the other side?
What do you mean the other side?
Like under the other speaker. It's like 9.27.
Like 9.27. All right, so Connor says, well, what about if instead of using the 6 foot as our straight length, we use the 4 feet, and then we have the diagonal run here.
Wait, the square root of 80 plus 6?
Yeah.
What did you get, Connor?
Make sure you're in.
I did the square root of 86.
Hey,
Okay.
Akshaya, another reminder for next week. Make sure that your calculator's in the right settings when you start to solve things.
Mine is just an endless I.
So you're in complex number form, not real number form. You want to hit mode. Come down here. Actually, mine's not. I don't even have one chosen right now. But because you're an A plus BI is why it's not going to spit you out the decimal. So if you hit real,
14.9.
it should spit you out the decimal.
It's actually like
So like 14.9.
It already did that when it was in the other one.
Oh, I thought you said it was giving your answer in A plus BI form.
No.
Oh, well then you're fine.
I'm
But
gonna put it.
But in your mode is where you change all that stuff, right? And radians versus degrees, very important. So then the other one is 4 plus. I don't know what's on the test. That's why I'll try to download you a review. I don't teach Math 1. Like literally, now that I don't teach the summer class, I don't teach
Yeah,
Math
I
1.
was mad at you that you didn't go to the
They
summer.
didn't hire me.
That was sad. I was so excited.
They didn't have the money.
That was
They could only pay one teacher.
14. Because that's a dilation of 3.5 times.
Ooh, you're right.
That is.
So that hypotenuse is 10. Okay, so that got a little better.
What if we try it just at the 7?
Just at the 7? Well, what if we try in the middle? Like, that's...
Well, that's not going to help us.
Why won't it help us?
I don't know. Maybe it will help us. Maybe we should try it in the middle. Actually,
Ah.
yeah, that'll help us.
Get out of here, news.
Okay, so it's 4 on both sides.
Yeah.
Wait, that doesn't look right.
It doesn't matter.
That should be a 4. It's fractal 2 times 4.
Doesn't matter how much.
What? Oh, because this is 4 and 4 and they should be equal? Yeah, no, so don't trust the scale of your axes are scaled differently here, right? So if you want to make this look better, you would need to change the scales of the axes. Oh, hey! That's in this menu we just looked at earlier in class.
Wow.
So if you wanted to change your y-axis to look a little bit more similar to your x-axis, or crap, I changed my x instead of my y. I don't know, do that till 12. Do this till 12. Negative 2.
What did you get, Connor?
Negative 2.
I'm still doing it.
Now your 4 and 4 look a little closer. Oh, it's this doodad is in the way. I didn't help. That did the opposite of help.
Yeah, I got 12.86.
Alright.
That's because our screens aren't square. Can we just not care what it looks like?
Yeah. What if we made it a 3, 4, 5? I don't know if that would help.
So make this 3.
Yeah, no, but yeah.
So wait, what was this? Was this more or less than 14?
It was a lot less.
What was it?
12.87.
Ooh, 12.87. Okay, that's getting better.
Well, if we move it to the 3, then or
All right,
the
try-
5.
Or the 5. Well, that lets us do a 3, 4, 5, right? So then this is just 5. So you only have one hypotenuse that we need to solve. I feel like
12.81.
we kind of keep swinging back and forth of like right now purple's longer than red, right? And like at some point red is longer than purple.
I think we want it to be equal.
You think we want them to be equal? I don't exactly know how to make the hypotenuses equal to each other.
Unless.
I feel like it'd be somewhere like around here.
No, it'd be.
Other way? No, I think we need to be closer here because this goes higher.
Yeah.
You want me to try this 3? We tried 3 away from the other
I
side.
think we should try 3.5.
3.5. Try that out. I don't know that we want the hypotenuses to be equal because the triangles aren't equal. Right? Because Laura's silly and she's going to mount her speakers at 2 different heights. The nice way to say that is silly.
No, it's not. It actually hurts my feelings more when someone calls me silly.
You'd rather be called dumb,
Yeah,
which also isn't accurate.
exactly. I know I'm stupid.
Guys, I like, not trying to make them feel bad, but I can't believe you aren't figuring out what would be the ideal situation.
Put your speakers at a normal height.
We can't do that! Laura told us this is what we're doing.
With the thing higher in the air.
Okay, to circle this back to Akshay being mad at me, last summer, how I made my money is doing random jobs for people. You can't walk into a job for somebody where they say, I want this, and say, well, you're dumb, I'm doing this. You can't do that!
You can
Laura
say
wants her
yes.
speakers there.
Okay.
Her loss.
It's your loss if you don't do the job.
Wait, it's 12.9. This side's worse.
Oh, this side's worse?
Yeah.
So you're saying we probably need to be on the right of the 4?
What if we did 4.5?
What if we did 4.5, Akshay says?
I don't think that would help.
The way that you're saying is
Don't we want the hypotenuse equal?
We don't want them to be equal to each other.
wait, we can figure out the distance between the 2 speakers. That might be useful.
How would that be useful?
I don't know. Square root
68.
68. Looks like 8. Wait. What's we have that? What if we play at 4?
What ends up determining how long a hypotenuse is compared to the length of the cabinet? Right? What's going to determine like the length of purple and the length of A? Like,
The length of the legs.
well, the legs stay the same, and this total distance stays the same.
But the one leg changes.
Well, the hypotenuse, well, yeah, so the base leg changes.
The
But then
angle-
as I make this base leg longer, this base leg conversely gets shorter.
It's Hinge Theorem.
What is Hinge Theorem?
The hypotenuse angle up there, like on the side, like that, and then it pinches together closer, and then it makes a smaller triangle, and then when it goes like that, it makes a larger triangle.
Okay.
The triangle
So you guys keep saying make the hypotenuses equal, and I keep saying no.
You're saying we want it to be as pinched together as possible, then?
I think what Jake is saying is we want these angles to be small.
No, the angle's next to the speakers.
So here I've made one, they're both acute, but I've made one very acute and one closer to 90. And you guys said that was worse. We came over here and made like one real acute and the other one closer to 90, and we said that was worse.
Well, what's better?
This was better, right in the middle.
And when it was on at
Five
5,
is
it was
really
even better.
This was better.
Wait, move it over just a little bit, like left. No, right. Yeah, there. Yeah, like there.
Wait, what if we use the angles?
What?
Similar triangles.
So what if we made the angles of angle of elevation, right? The angle of elevations here. What if we made them the same?
Yeah, that's what I'm saying.
How could we? Well, I don't even know the angle measure here.
We have to make them similar triangles.
Okay, so if we have to make them similar triangles, how do I know where to put
Why do we
this?
have
You
to
need to make the base of purple, or no, you need to make the base of red 2/3 of the base of purple.
I need to make the base of red 2/3 of purple. So really, there are 6/3.
1/2.
6/3 is 8. No,
Yeah.
wait.
6/3 x is 8.
Okay, so 6/3 of something is 8. So we need to figure out what the 2/3 is, and then the 4/3 will be on the other side. Because 6 and 4 would make 10 total parts. We're throwing around too many numbers, but I think I know what you're saying.
5/3. 5/3 equals 8. 5/3 x equals 8.
Yeah, okay.
And then
Okay.
x is base of purple.
No.
Yes.
Wait,
So what
yeah.
Jake is saying is that this leg will be 3/2 or 6/4 of this leg. Yes? Yeah. Or like an extra 33% or an extra whatever. Okay. All right, set up the ratios and tell me where we should put this.
It should be at 4.8.
Is this called something?
It should be at what?
4.8. 4.8.
I've looked at too many lesson plans today.
So it should be at 4 2/3.
No, 4.8. That's 4.8 divided by 2 times 4 equals 9.6. No, wait.
Hold on, I'm thinking.
Okay, 8 divided by
5/3.
So what you're saying, Connor, is that 4.8 compared to 6 is equal to, what would this length be then?
Yeah, you're right. It is 4.8.
3.2 over 4? What's the sum of those hypotenuses?
Oh,
That would make similar triangles, right? Here, 4.8. Here, 3.2. If I compare these, oh yeah, this is like 16, 32, and 48, right? Like 1.6 over 2 if I start trying to like simplify, like 16, 32, 48. These are similar now. This is how you would optimize this situation. To get those hypotenuses both as short as they can be, we want to create similar triangles so that, kind of relating Hinge Theorem, that wasn't even my plan, but kind of relating Hinge Theorem, that will then make the distances like optimized, right? Like the least possible. Good work. I think it's time for lunch.
Can we put up
Here's another problem that you can solve just if you feel like it. If I give you a cube
Oh, okay.
with edge lengths x, What is the distance from the front bottom left corner to the top back right corner? And this is where we're going to pick up tomorrow.
It's x to the third times x to the third. It's the cube root of x to the third times x to the third.
I have no idea what you just said.
Plus x. It's the cube root.
Wouldn't that just be x plus x? Or no, because you can't split up addition of powers. You can split up multiplication of powers under a root.
Oh, yeah, sorry. It's x to the third plus x to the third. The cube root of that.
Do you know where the large conference room is? Because I don't know where that is. That's what I'm taking my test.
I have
Are
a
you taking the test
guess.
today?
No, it's next week on Monday.
I have a guess that it's in the office,
Okay.
but I'm not sure.
Wait, is it here?
Yes.
I would hope it's here.
Is anyone else checking it? Or is it
I don't know. There's probably somebody from Perry that needs
I
to.
didn't see anyone that I noticed there.
You'll just
It's
have
what?
to find the
Square
square
root of 3x squared.
But I think what you and Connor said is different.
Yeah.
That's what I'm thinking is.
You guys know it's time for lunch, right?
Yeah, I know.
Shay's like, I'm out of here, people.
I'm hungry. So Connor, what I'm thinking is, we have to do 2 triangles to get to the line we want. And then one of the triangles is this one here. And then one of them is this one here.
This is hurting my brain.
Oh.
Because colors are
And then we have to
layering.
get
So
hypotenuse
it's
of
x
this.
squared plus. I feel like it'd be easier if you just gave us a number. Can x equal 1?
One's going to be bad to work with. You should make x anything but 1.
Anything but
1?
X equals 10.
1. Radical 2.
You're so dumb.
Radical 2, and then this also has to be radical. And then that's 1.
I was
So
about to say,
then-
that's not radical 2, that's 1.
Radical 2 times 1?
But wouldn't it be that
radical
squared
2
times...
squared. It's 2 plus 1 squared. It's radical 2.
Connor.
And this is why
Jake,
I
it's
started
radical
high
three.
school math.
Wait, you're saying that if we made a 1 cube,
Yeah.
the diagonal across the bottom is radical 2, and the diagonal across the entire cube is radical 3?
Connor, you're dumb.
Nope, that's right.
Hey, don't call people dumb.
It's
So
right.
I was not meaning it.
You were not eating it.
That's...
I'm gonna be in the family room.
So I think you're like almost all caught up, aren't you?
Yeah, I just have to get some homework from like last night that I couldn't get done.
Sweet. I'll circle around and see if you need any help.
Jake, it's radical 2. Now, that's just 1. Oh. What? Jake, it's
The square root of 2 times x squared. I think that would just be radical 2 times x, which if x is 1, then I think Connor's right. It's just radical 2.
2x squared.
Right, but you can split that up, right? You can split that up in radical 2 times radical x squared.
I'll be back. I can cross the homework.
It's
You
just
square
radical
that
2
with
times
that.
x.
And no, you don't. It's not 2x squared. What's the square root of x squared?
X,
X. And what's what's the square root of 2?
radical 2.
So it's radical 2x, right? Which if x is 1, I think what Connor said is right. It is definitely time for lunch. I'm just going to say it again.
Radical 3x. Which means I was wrong the first time, but not when I was proving it.
We're going to start with this tomorrow.
No, we have to finish it right now. Jake, you're just making it too complicated.
I think you overcomplicated it. I also can't keep track of your work because your writing's a tidbit sloppy.
Yeah, I'm not good writing on a vertical surface.
I know, it takes a while. It's real weird at first. And then eventually, like, writing on a flat surface gets weird after you've written on a vertical surface long enough. Alright, now I can save this and we can leave.
I think it's radical